Welcome once again. In the previous video, we learned about Sn2 reactions and then what are some qualities that made up an Sn2, and then we did some problems, and then I had you work on a practice problem. Now we're going to focus on Sn1. As I said, Sn stands for substitution, nucleophilic, and 1 is unimolecular. What does unimolecular means? As with the previous case, you have a substrate containing a leaving group, and then you have a nucleophile. The nucleophile attacks the carbon containing the leaving group, and it gets substituted, and you have a product. Now, unlike Sn2, Sn1 is unimolecular. That means the reaction only depends on the concentration of the substrate and does not depend on the concentration of the nucleophile. So that's a direct opposite of what Sn2 was, right? It included the concentration of both the substrate and the nucleophile. Sn1 just depends on 1. And unlike Sn2, Sn1 reactions are not considered. That is, it happens in 2 steps with an intermediate formation. Okay, I'll talk more about it because that's a very, very important idea. And Sn1 reactions are typically carried out in protic solvent conditions. Sn1 reactions are typically carried out with weak to moderate strength bases. Strong and bulky bases are definitely not preferred. Okay, weak as in water, NH3, all of the weak bases are shown on the bottom. Neutral bases is what you would use for Sn1. And Sn1 substrate reactivity is, it's the opposite. Tertiary substrate, carbon that's tertiary containing the leaving group, has the highest reactivity for Sn1. And if the carbon in the substrate, secondary or tertiary, is chiral, and then you have to carry out an Sn1, that it results in a racemic mixture. That is, if you start with an R, you'll end with 50% R and 50% S. Okay? And the reason I put this point at the very end is Sn1 reaction involves in the formation of a carbocation, which directly relates to this intermediate formation step. That is, an intermediate in this case is the carbocation. I'll show that in the next step. Okay. So here's my substrate containing the leaving group, and you see this is a weak base. And it's carried out in a protic solvent, right? This is my protic solvent. And this is my weak base. And this is my substrate. And this is my leaving group, right? Now, we'll worry about R or S later. What I mean here is that the reason it only depends on the concentration of the substrate is this is a secondary substrate, right? Because it contains hydrogen. 1 hydrogen, so it's secondary, right? So the way Sn1 mechanism works is, because right away there are some clues that tells you whether it's Sn1, it's a weak base. It's not a bulky base, it's very weak, it's protic solvent. First, the leaving group comes off before the nucleophile even attacks. That leads to formation of what is called a carbocation. When the Br leaves, it leaves a positive charge. Okay. Again, I'm not drawing the entire mechanism here, but the Br leaves first. This is called a carbocation. And usually, if it's an intermediate, it's put inside a bracket. So this is a step that you have to go through. Unlike Sn1, where both the attack of the nucleophile and the departure of the leaving group occurred at the same time, which is what called conceded. In this case, it's not conceded. The leaving group leaves first, and then the nucleophile attacks. Okay, which is the O attacks here, and then leads to the product, which is basically the same thing as previous case, but then you'll have 50% of, see, we don't need to even worry about whether this is R or S, but the product is easier. We still have to determine, you have one where it's swapped, right? One where it stay the same, right? Plus the other it's swapped, right? So if you use the chart for this one, these are the two products we have. Basically, the Br is replaced by an OH. So if you, here we have 1, 4, 3, and 2. So that's clockwise and back is R. So we have started with an R, right? So we'll end up with, well, 1 will be, this will be 1, 4, 3, and 2. So that's clockwise back. Again, this is R. And this will be 1, 4, 3, 2. That's clockwise front, which will be S. So you'll have two products, and this is why it's happening. This is the intermediate, because it makes results in the formation of a carbocation. And the way you write the rate of the reaction is rate equals K times only the concentration of this. Or you can write it as K times, there's 1, 2, 3, 4 carbons. There's 3, 4, 6, 9 hydrogens and a Br. And that's all there is to an Sn1. And I've done one more. Basically, in this case, if it is NH3, this is the only exception, and that's why I chose to address that. Same thing, the Br leaves, right? Results in the formation of a plus charge. You still have the hydrogen, right? That's still there. This is the intermediate carbocation. And then the NH3 attacks, right? It contains the lone pair. It attacks the nucleophile. Now, you cannot have OH, okay? This is a protic solvent. This is a weak base. You cannot replace, or you cannot always put OH. In this case, you have to just leave out. In water, we left out a hydrogen. We ended up with OH, right? Similarly, in NH3, we have to leave out a hydrogen. So we will end up with NH2. So we will have two products where NH2, it stays in the same open and close, plus in the other case, it's very difficult to draw these things with my pen. You probably already noticed that. So this we already said is R. So this will be also R. This will be S. Okay. And the rate will be K times same thing, C4H9H9Br, or you can write it as the structure itself. Right? Very good. So that's Sn1, and I have a practice problem for you, and I want you to solve these. And then I'll see that in my thoughts. I'll see you back with the nucleophilic eliminations, which is a newer topic.